So lecture number 17, we will talk about acoustically large space. Corresponding chapter is chapter 5. The book which you are taking as a textbook. Today we will talk about a very large space, meaning that the characteristic lengths of the space is very, very large compared with the wavelengths of interest. Okay, mainly we will introduce Savin's theory, which is very famous and well-known theory that describes the quality of room or characteristics of room, which can be regarded as acoustical large, can be measured by simple time constant, which is reverberation time or reverberation period. I think I already mentioned very briefly what it means, but today I'd like to derive this, okay, and I will conclude this will be 0.161 and the size of room and open area window. AS can be regarded as summing up all the absorption coefficient and the area of the surface. And let's see how we can get this result. Under what kind of condition we can get this result. Okay, suppose we have a room that look like this, and maybe in the lecture hall you have stairs and you have some seats, whatever, and those can be regarded as, for example, some surface impedance, say Z1, and you have another surface Z2 and probably some other surface G3 and so on. And suppose you have orchestra playing over here that radiates sound, and this sound will meet the surface distribution of impedance mismatch that I denote here G1, G2, G3, and it will, of course, will be reflected back and forth like that. So eventually all the sound will be mixed up in this space. So if you look at the energy, that is, of course, in general, function of space and time, it is consisted by two components, as we know. One is the kinetic energy, which is 1/2 rho zeta v square, and the other one would be what we call potential energy. This is just the energy we derived by squeezing the unit volume of compressed air, and then we can find the kinetic energy by squeezing the unit volume of air by the pressure. We will get this result. Okay, and if you see the certain volume over here, delta V, within certain period of time of this energy, then I can see that sort of mean energy inside of this volume and during that period of time could be regarded as 1 over delta V integral dV, and then I also take the average with respect to time from t to t plus t. T, capital T, is the period, I mean time duration that I'm going to take an average, and E are T dV. Sorry, I used the T dV already. If you look at this energy, which delta V is very large compared with wavelength cube of interest, and lambda is wavelength, and also the T is large compared with the frequency that I have interest, then this energy would be like this energy would look like, indeed, in space, if this is the space from the sound source, then will look like very much constant if I am very, very far away from the sound source. For example, I'm singing over here. What kind of song do you want to hear from? Okay, I didn't prepare this demonstration this time, but maybe for example, if I sing like a 나의 살던 고향은, right? Then what you hear over there and over there is sort of summing up all the kinetic and potential energy, and what you hear, for example, over there and over there would be, in some sense, very much in average sense, average with respect to that volume, and average with respect to the period would be quite constant. So look like that. And then at some stage look like that, because if you are close to me, then what you hear would be different with what he can hear. So there could be some fluctuation. And then at some point it would look like that. From here to there, what you hear is most likely direct wave. So I call this is direct field, and I call this field reverberant. from here to there I call reverberant field, and I call this field diffuse field. Okay, that's very important concept. Okay. Or you could say SPL would very much similar. So in direct field, sound pressure level would decay 6 dB per octave. Octave means by increasing twice of the distance, the sound SPL would decrease by 6 dB. Okay? So if this energy is diffuse or satisfy diffuse sound field, then we can say the following things. Okay, also note that the rate of energy change with respect to time has to be balanced by intensity. So if you apply this equation to one-dimensional case, if there is some impedance mismatch over here, say Z1 and Z2, and if you supply the sound by using speaker over there, then some energy will go out. So rate of increase of energy has to be balanced with what coming in minus what coming out. What coming out is smaller than what coming in, then dEdt will be positive. But if what coming in is smaller than what coming out, then dEdt would be negative. Okay? So expanding this idea, and suppose that we have a diffuse field as well as direct field inside, then we can write the following things.